Okay, now we're talking about resistance of a wire. Resistance of a wire depends upon two things. It depends upon the type of material it's made out of, and it also depends upon the geometry of the wire. So type and geometry. Now there are some things that don't conduct electricity at all, but it's really a sliding scale when we're talking about resistance. Now the formula for resistance is equal to resistivity times L divided by A. Resistivity is directly related to the material, and then of course L is length and A is cross-sectional area of it. Resistivity is a constant that varies for every material. So if we look at a table like this, and you'll be given a table like that at any point in time, and you'll get a table that looks like this. And what that does is tells you that not all things conduct electricity equally, which I think you already probably know. The resistive unit is ohms times meter, but that's not really as important as taking a look at the numbers. Out of these particular materials there, which one would conduct electricity the best? So in other words, the best is the one that conducts electricity the easiest, which means it would have the lowest resistivity. And silver, out of all of those, we traditionally use copper because it's cheaper, but we don't use it. They oftentimes use gold more as a selling tool than anything else, because if you look at gold, does not conduct electricity as well. Now, if we go to the other extreme, what are the things that have a lot of resistance? Well, if you have a lot of resistance, you're going to create a lot of heat. So therefore, the things that have a lot of resistance are going to be the things that we use to create heat. The two primary ones, nichrome number one, that's the highest number there. Nichrome is what we use in toaster elements and oven elements and like that to create the heat. Another one that we commonly use a lot to create heat is tungsten. That's what's used inside light bulbs as an old-fashioned incandescent light bulbs. Now for resistance versus length, it really makes sense. If I have that wire and that wire, A is of course going to have more resistance. The longer the wire is, the harder it is to push electrons through it. That makes sense. Now, resistance versus area. Now, key thing to remember is electrons hate each other. So therefore, electrons are going to run along the surface of the wire. They're not going to run on the inside. Matter of fact, in the inside, the E field is equal to 0. They don't go on the inside. They stay on the outside. So therefore, the bigger I make a wire, the more electrons I can push on it. So therefore, it's easier to do it the bigger the wire is. So this is easier. Now, easier in this case means lower R. Remember, R is equal to rho L over A. And that kind of gives them all to you. It's directly related to resistivity. It's directly related to length. It's inversely related to area. So if A goes up, R goes down. And if you think about it, a fatter wire is much, much easier to conduct electricity through. Matter of fact, wires are actually sold by the gauge of the wire. And the fatter gauge wire is going to make it easier to push electricity through it. So you're going to want a fatter gauge wire if you need more electrical current, because it's going to make it easier. A 28 gauge wire is going to heat up more than a 10 gauge wire because it's harder to push electrons through. Now there's two types of problems we're going to see. We're going to see computational problems, and we're also going to see changing variable types of problems. Computational, straightforward computation, do the math. A sample problem where you change variables is going to be one like the one written below. What happens to R if the diameter of a wire doubles? Well, if the diameter doubles, then we know that area is going up. So therefore R is going to go down. But we have to figure out now how much. Don't forget, area is equal to pi r squared. So therefore, if I double the diameter, I'm doubling the radius. Be careful with this one. It's 2 pi r squared. Okay, and remember, so area is going to equal that. So the area actually goes up by a factor of 4. So therefore resistance is equal to rho L over 4A. So therefore the resistance is 1/4 of what it was before. So that'd be a great sample type problem. We'll do some computational type problems in class. Hope this helped.